This toothpaste is really strange. But is it liquid or solid? A pea-sized bit of it stays firmly on the toothbrush, just like a solid. However, you can easily squeeze it out of the tube, which you could hardly do with a solid, only with a liquid. And what about this hedgehog? Pretty prickly, isn't it? And now? It's much cuter like this. Try to run in a pool filled with a cornstarch water mix. Just try to walk slowly and you will sink right away, like in any liquid. But the mix resists if your steps are decisive and fast, just as if it were a solid. So you can walk, or rather run, on the surface of this strange fluid. In a highly successful Terminator movie of the 90s, a robot with a metallic body flowed through the prison bars and glittered like mercury. This villain transformed himself in the blink of an eye from solid to liquid and back. This is no longer fiction. Such materials are now reality. Just wait, and everything will be clear about these exotic materials. Let's start with the basics. What do we know for sure? No one doubts that water or oil is a liquid at room temperatures. They take the shape of their container, and their surface changes freely. And although a fluid cannot be compressed, its particles can freely move inside. Iron, on the other hand, is obviously solid at room temperature. The cohesion between its particles is so strong that the material keeps its shape. The relative position of its particles is almost constant and hardly changes. But let's grate the metal and mix the, still solid, iron powder with some vegetable oil. We get thereby a so-called magneto-rheological fluid. It can be freely stirred and poured, but place a magnet nearby, and the mix instantly behaves like a solid. Why? Because the magnet arranges the tiny iron grains in the oil as if they were particles of a solid. Recently, such materials have been applied in the most expensive sports cars. Their shape can be quickly and easily changed for superb drivability. According to experience, the solid or liquid nature of a substance is decided by the bonding of its particles. If the particles are ordered and do not move when external forces act, then the material is solid. If the particles are bound, but external forces can move them, then the substance behaves like a liquid. This flow property of materials is characterized by their viscosity. The word comes from the Latin viscum, which means a sticky paste made of mistletoe. Back then, it was used for catching birds. Viscosity is essentially a proportionality factor between flow speed and the force causing the flow. If the force and speed ratio is constant by all circumstances, we are talking about a Newtonian fluid. In all other cases, the fluid is non-Newtonian. Come on, non-Newtonian? How can anything exist that is not Newtonian? After all, Sir Isaac Newton was probably the most famous physicist ever. Everyone has heard about his laws. These are the basics of classical physics. Or not? Well, the fact that a fluid is non-Newtonian doesn't mean that it violates the laws of mechanics. Besides laying down the fundamentals of mechanics, Newton also established the law of viscosity. According to this, the deformation rate of certain fluids is directly proportional to the shear stresses. To put it more clearly, in such materials, the flow rate is proportional to the forces acting on them. If the force doubles, the material flows at twice the speed. On a diagram, this behavior can be visualized by a straight line, starting from the point of origin. As mentioned, water or cooking oil are, among others, such fluids. Substances that behave this way are called Newtonian fluids, because their behavior can be described by Newton's law of viscosity. But for materials that don't obey Newton's law of viscosity, the force and speed function is totally different. Ketchup, for example, flows more and more easily when you increase the force. Bad news for your t-shirt. In this case, increasing the force creates a more than proportional flow rate. That's why such substances are called power law fluids. If the exponent of their power function is less than 1, then we are calling them pseudoplastic materials, like a paint or nail polish, which spreads easily when applied with a brush but flows less if already on a surface. And now let's see the cornstarch slurry again. Since its particles align themselves due to the movement, they get closer to each other, so the material needs an increasing force to be moved. The relationship of flow velocity and force can still be described with a power law function, but its exponent is more than one. Such substances are called dilatant fluids. And what about toothpaste? Its microparticles are tightly bound at the beginning, so the paste can't flow out of the tube. However, as we overcome this initial resistance, the fluid begins to flow. Any extra force speeds up the flow. Mustards or mayonnaises are a good example of such plastic fluids. Of course, the relationship of force and shear rate can also be linear for some fluids. These are the so-called Bingham fluids. Eugene Cook Bingham was one of the pioneers of investigating the non-Newtonian fluids at the beginning of the 20th century. His name is preserved not only by this type of fluid, but also the Medal of the American Rheological Society, which is awarded annually since 1948 to an outstanding researcher of the field. As you've seen, these materials are interesting in many ways. Although they have been studied for over 100 years and have more and more practical applications, they may still have vast undiscovered potentials. In Spain, for example, smart speed bumps have been patented. These are filled with a non-Newtonian fluid that becomes thicker on shear. If you drive slowly, the bump stays soft, rewarding thereby the cautious driver. But a speeder collides with a hard obstacle, causing his car to bump. No doubt, this is unpleasant both for the passengers and the shock absorbers. The development of a new bulletproof vest was a further big engineering achievement. The space between the Kevlar fibers of the vest is filled with a shear thickening fluid, so the vest doesn't hinder free movement. But if a projectile or shrapnel hits, the fluid instantly hardens and prevents serious injuries. So how can we decide the solid or liquid debate? Well, following good engineering habits, the only answer is, that depends on what? On the circumstances. In other words, these materials are all liquids, but they have special flow properties. That is why they behave sometimes like solids, but sometimes like liquids.